Okay, so thank you for coming to this talk again. And well, you know this slide already, so I'll skip it because we talked about it yesterday, my role at Oxy. But today I will be talking on the details and in depth about my latest research. And specifically, I shortened the presentation a little bit in order to have more time for questions and make it a little bit more interactive. The presentation is divided into two chunks, let's say. So the first one is about the computational system Vivo, and the second one is about my research on music and motion recognition specifically. And also I understand there were some confusions that and I took notes from yesterday, so I'll try to address some of these. Okay, so as a first thing, let's recap what's the methodology behind most of my research. From an interdisciplinary perspective, I use performing arts as a framework. And that includes music making and listening, visual sequencing, and motor planning. Sorry, the reason I work on these different domains is because they have things in common at the level of perception and cognition that work for me and that worked in my research. So I will talk specifically about music, but somehow this can be referred to the other domains. Let's start from the action-reaction cycle from Le Mans, University of Ghent. And what you see here is exactly that in the refined version from Keebler. This describes an interplay between two musicians, for example. So the first moment is the moment of listening, when receiving and processing the vibration of sound, so the acoustic vibrations. Then there is the moment of judgment based on physiological and cultural constraints. And to these, I would like to add the personal level, which is how Bergson defined. So we have the universal physiological, the cultural, and the personal level at concentric, one side the other. And then after the moment of judgment, this goes into a change, which is a change of physical condition to optimize the future judgments. And this leads to the reaction moment, which is the moment of playing in response to the listening. And so this rinse and repeat continues. The same principle can be seen differently from a slightly different perspective, what we call action perception feedback loop. That's very useful when we talk about implementation. So the same can be applied basically to human-machine interaction, of course, with the proper differences. And what I was mentioning yesterday, which is the analysis of semiosis in the human music interface, and specifically mentioning Gino Stefani, which was a great semiologist. This was important to somehow introduce again what is the interaction model of a Vivo user instance, and so that we have it clear. I wanted to clear some doubts yesterday. So we have music making by the user. This is analyzed in terms of video and audio input, and is passed to the generation of Vivo, which goes back to the listening of the user. So again, we are expanding that action-reaction cycle here in Vivo, basically. And it's a type of cross-modal interaction because there is more than one mode involved, because there's audio and video, and they are both meaningful to the generation. I'll go fast through the system architecture very quickly, but I'm happy to go back to any of these and please ask questions. It's what I call salience of action, which is essentially computed as the variance of the quantity of motion. It's a time-based variance. And we have a threshold that is triggered every time the salience of action surpasses it. This information is passed to audio processing sequencing in the processing component, but also is passed to the interface component. There is an editor for scores. Specifically, I'm talking about stochastic scores. So it's parametric scores that are controlled by chance. There's a random control of the parameters that can be defined. And then we have a network component that can allow for different type of operations. And of course, outcome as audio only. So in terms of what happens, we have extra musical information that provides a simple salience-based model of the user-system interaction. And this is used to simulate intentionality. And I specifically use the word simulate because, of course, intentionality has multiple layers. This is the PhD thesis. This is the release from the University of Kent under the GPLv3 license, the third version in 2014. But the key article that I'm referring to, and I will links this afternoon for you to check the research more in details, and happy to accept criticism and feedback. The article Creative Autonomy in Simple Interactive Music System. So we'll go to something of this in this talk. And specifically, the system works leveraging on expectation. Musical meaningfulness is a term that to describe phenomena where the user expects a meaning in what is perceiving. And this has to do with what I was briefly mentioning yesterday. There is an expectation for coherence and intentionality in the observation and perception of the world around us. Okay, I'm going to skip now to a video. And the video is the same that we watched yesterday, but this time is shorter and there are comments on it. Understand a little bit better what's going on in here. A little bit of more words about what are the findings that led to this article. So the question is, can autonomous systems be musically creative without having musical knowledge? And the research is based on assumptions from interdisciplinary studies on self-reflection. I mentioned yesterday that there is a specific class of interaction that is named reflexive interactions at play here. And these are evaluated with the system, as I mentioned yesterday, in a number of different projects and case studies. So the system is able to generate material, is able to have creative autonomy. Now, what do we mean by creative autonomy? That's very important. And this is what I mean specifically. The system generates material that is novel, primary, and contextual. Let's break it down. Creative autonomy. When I talk about autonomy, I mean independence, not necessarily free from external influence. And I'm referring to Brown here in computational creativity. For what is novel and primary and contextual in vivo, let's talk about it for a little bit. The material that the system generates is novel because it is different and highly different from what the musician has provided as input. Now, you may say, well, that's an easy win because you are processing an acoustic sound to obtain an electronic sound, which is on a different dimension. Well, that is exactly the point. But also, we can extend the scope because in vivo we lowered audio processes that elaborate the sound in real time, and these plugins are VST technology, which is a standard for audio processing. But the way the system uses these plugins really allows for nuances that really hardly achievable by hand. And an example of this is in the music album I linked yesterday, the electroacoustic bonding, because that contains human-human interplay. So with the same algorithms that are being used for processing, and also one piece, that a very early piece with the Vivo system. It is primary because, as we saw in the video, the trombone player, it is primary because the system can initiate the action and the human interplayer can become follower. So it's primary material in the sense that it's not an accompaniment, it's not something that comes along with it, can be a first voice. And it's contextual because the material, being an elaboration of the original one, maintains context. And novelty, it's achieved not only by, of course, processing of the audio, but by The fact that we have a video analysis on the subjects the musicians playing is providing these two types of input that allows the system to actually have these three components. I would like to highlight and then have a break with you that we have here a bare minimum. That was the key point. That's why a simple interactive music system, because we have a bare minimum of creative autonomy based on the capacity of the system to identify musical salience in the material that is generating, and for the system to act as an autonomous musical agent. So I hope this clears a little bit confusion that I might have created yesterday about what exactly the system does. And also I would like to point out, it will become clear in the second section of the talk, that emotion recognition is not implemented in this version of the system, and that Markov chains are not implemented in the version of the system that you saw. These two components are completed, like the Markov chains has been developed for the Max MSP environments, has been a lot of work using abstractions from the IRCAM library, while emotion recognition, I will talk in details later. This was the first section of the talk, and if there is any questions or comments, I'll be happy to try answering. I will skip this slide. It's the same as yesterday, and go to the details of the dataset, comprising solo dance improvisation. There is more than 100 acquisition, 3 minutes each, total duration more than 5 hours, realized with 10 professional dancers from UCI, Creative School of the Arts. The dataset is released in its first version on GitHub at this address. I will send you links later. So there is an interactive sound generation that you already saw in Vivo, and Vivo is used to generate the audio counterpart of the clips. And I'm using what I was mentioning before, the GRM tools from INA GRM, granular synthesizer, multi-resonance filters, multiple delays. These are 3 techniques that are kind of common in electroacoustic. There is mock-up components in the dataset, realized with a 30-camera Vicon system. You can see here the cameras. And we are using 53 marker silhouette for the acquisition. In terms of video, we are using a green screen digital video capture environment, which is the one that you see here in the background. There is a nice bouncing floor for dance that makes this environment kind of unique, honestly. The video acquisition was in 120 frames per second at full HD quality, APC-C sensor. This is the bodysuit and the sensors attached, and you can see here the Blade software from Vicon. Gives you a little bit of an idea of the painful work of acquisition was carried out. So it's a lot of work. The first version of the dataset requires some cleanup at the level of the mockup, but I will show you now what is the mockup that we have, and it's not that bad, to be honest. There is some language modeling used for the interviews to the dancers, and there is a game with a purpose that I designed, drawing from Lisa Pearl work, mind-print-based game with a purpose. It's a system used to define the annotations and validate the annotations to be used for the learning process. It's a gamification experience. There is a link here if you want. It's kind of broken right now because it's not being used anymore, but I guess you can check it. And these are screenshots from the game with a purpose about how this works. Basically, there is a snippet of text, an audio clip or a video clip can be annotated. It's available online. Now, there are multiple ways to categorize emotions, and this, I was saying before, is kind of the Pandora's box. It was much harder than I thought working on emotions. Let's recall these points. Different subjects can have and generally have different opinion about the same emotional content. And we are specifically talking here about induced emotions or expressed emotions. The music has some emotional content, and this is perceived differently subject to subject. At the same time, because the experience is interactive, the dancer is generating the sound by dancing. The dancer generates sound because Vivo is watching them, and this generates the soundtrack for them to dance. There is this feedback loop of information that I mentioned before, ongoing continuously, which affects everything. We have multiple annotations for each piece to be annotated, of course, so it's a multi-class problem because we can have more than one class for each piece. And then we have continuous values representing different dimensions of perceived emotions. I'm referring here to the most common valence arousal circular model of affection, but we also use dominance, which is the third dimension. And of course, a dictionary of patterns that appear in the sample data on a short-time scale. So we sample the data at short-time scale. Pattern can express the emotional content of a music file. The algorithms are run not on the musical mood dataset, because before developing the dataset, we actually develop the algorithms and test them on the Emotify database. So the Emotify database use the gem scale, which are multi-label. They accept more than one label per each annotation. I will go a little bit fast here and not go into all the details, but again, I will leave you time to make questions and we can go back to the specific slide. And also I will share the articles. It was just published at the beginning of last month at the Tripoli conference. We have a few problems here, of course, when we run into this multi-level, multi-class type of learning. This leads generally to sparseness because few annotations per track. And so the way we approached this was actually to identify plateau zones in the Emotify database. Plateau zones are basically percentage of consensus threshold that we estimated a posteriori observation from the average trend of the emotion per track in the dataset. We have a plateau zone at 30% with an average minus plus. These are a few details about the feature extraction component. We are talking audio only. My work is not on emotion recognition on visual. I've never done that. My work is on computer vision in terms of feature extraction and on motion capture. So I've done feature extraction for motion capture, and we're using MATLAB and Toolbox. So the feature extraction that is run here instead looks at acoustic features, so intensity, rhythm, timbre, and psychoacoustic features and melodic features more inherent to the music itself. And then the classic statistic features that can be computed from the other features. A little bit about what goes on in terms of achieving best results here. We have a discretization algorithm that we use as a stopping criteria. And we also employ correlation-based feature selection as a feature selection method. And we are actually classifying on 9 different emotional labels. And the labels are non-exclusive, though that's why it's multi-label, and can be present or absent for each music track. And therefore, we are in a multi-class problem. The machine learning algorithm employed here are mostly the support vector machine using an SMO kernel and a Bayesian classifier using a simple estimator, apologize. And we use as a neural network, a simple neural network with 50 neurons in a single hidden layer. Let's go to the results. This is the comparison table for the difference between the classifiers within the original Emotify classification study. And as you can see, we actually achieve higher result when we use the discretization in combination with the correlation-based feature selection, which hit 80% of accuracy. Now we'll go into the details of this. Of course, this changes a little bit for each emotional label. This is just an image. And this is the root mean square error comparison. On the left, we have the root mean square error for each method employed in the original Emotify study. And then we have our methods under the 3 different classifiers. Now, you can see clearly that there is an improvement in root mean square error with the original classification study, basically for all the different labels. So some considerations to sum it up and leave 2 questions for you. So in the Emotify database, in the original study, Emotify, they highlight a same pattern of success and failure, suggesting that amazing and joyful activation might be emotional categories subject to strong variation out of subjectivity. But we cannot confirm that from our study because instead we actually report a high accuracy for both the emotions. Instead, we have low accuracy for solemnity. We can draw considerations here on personality, culture, or denotators. But again, I like to consider these studies preliminary in a way, because I really want to see what happens when we actually apply these algorithms to other data sets, such as the musical moods, or when we apply other algorithms to our data set. So just to recall it, this is the mean accuracy achieved using the best classifier, and that's the improvement in terms of RMSE. And before closing, I like self-critic. I constantly trying to challenge myself and having fun of myself. Why computational creativity? Because we can. Because I have a will of power, maybe, as Nietzsche said, and that's not necessarily a good thing. Maybe it's not a bad thing beyond good and evil. Maybe is to extend our creative capacities. Because I can't. Because I'm an unsuccessful or untalented artist, but I cannot give up on that dream. And I'm talking personally, right? So because the intrinsic value of music is really currently on the low, and I'm really being not nice here. Maybe there is too much garbage music around, or maybe it's just commercial. That's the way it is, you know, and it's Art in This Shadow. It's a wonderful book, I recall now. But is it really so, right? Is it really garbage music? Or one is functional to the other? And then, you know, we can say that current musicians maybe are actually overvalued. Successful, famous, you know, the mainstream, because the mainstream makes the trend in a way. But we could say a machine could do it just as good or even better and much cheaper. Because I seek novelty per se. Again, this is not necessarily a good thing to seek novelty per se. I remember when Ezra Pound was mentioning, you know, novelty as a value, and this considered today novelty a value in the definition of computational creativity. But is it a value? I mean, it's a question, right? To facilitate access and lower the learning curve to music making, everyone can be an artist. I kind of believe that, but friends of mine do not. So it's really open discussion in a way. Because I need it, because I need to make computational creativity. Why? I don't know. Marshall McLuhan was saying, talking about extension of the physical body, extension of the nervous system. that every capacity that we achieve through technological means is an extension of physical body or nervous system, but comes at a price. And the price is an auto-amputation of another capacity. I'll make a brief example. An example I used to make years ago, I was teaching in a primary school. The wheel is the extension of the rotative capacity of the foot. And this allows us to walk faster, longer distance, get less tired. Fatigue is the main problem. What are we auto-amputating here, though? Well, I'm not a great walker, I can tell you. And our ancestors, for sure, and we know, we have research, were much better walking. So the question is, what are we auto-amputating collectively? Are we doing something about that? Do we want to do something about that? I don't know. Maybe it's just the way it is. To gain insight about such systems and or ourselves, that's the classic set, experiment, and observe, right? And we develop the system in this case, we set it and observe. Or maybe because I cannot bother with math and chemistry. So this was really the funniest alternative I could come up with, you know, and this is the mathematical foundation of music behind. Or that's something I like when I feel very blue and gray, and that to save what makes humans so special once we will be gone. Because creativity is a most important capacity of human evolution. Out of boredom also is always an option, or just because it's beautiful. And thank you.